In this project, I explore the use of deep convolutional networks and self-attention to learn a mapping from simulated quantum Monte Carlo imaginary time data to physically measurable real-time functions. In particular, I look at the current correlation problem, meaning the data used is designed to approximate an experiment investigating the behavior of current in a material. I won't go deeply into the physics of the problem here, though more details can be found in the adjoining paper. Suffice it to say that quantum Monte Carlo calculations are one of the main tools used by theoretical physicists in areas like condensed matter physics to carry out research. And the problem I am undertaking seeks to address a representative problem encountered when trying to use quantum Monte Carlo calculations to make predictions about real materials. Making progress on this problem would be a significant contribution to the field. Very basically, the problem framing is that I am trying to build a neural network which, given an input function lambda, representative of quantum Monte Carlo simulation data, predicts the set of parameters used to define the real function sigma associated with it. In some archetypal cases, the behavior of a material is dominated by a single, theoretically well-characterized process, for which a functional description of the measured sigma and the corresponding lambda are known. More complicated and interesting materials display properties associated with more than one of these archetypal processes, making them hard to predict. My insight in developing this project is that rather than trying to solve the hard problem of guessing lambda from sigma, we can rather guess a set of simple component sigmas which, when linearly combined, yield the true sigma. Thus, each example in my dataset is a lambda represented as a linear combination of 3 sigma functions. Each of these sigma functions is itself defined by 3 parameters. Collectively, these 9 numbers form a label. On this slide, you can see some pairings of labels along with what the lambda and sigma functions would look like when plotted. The numbers plotted in the lambda graph are the features which, in matrix form, would be fed into the model. There are 10 lines in each plot, as each function is plotted at 10 different temperatures. Consequently, the input data contains information about lambda at all 10 temperatures. The 4 different boxes each represent a different distribution from which the sample lambda label may have been drawn, giving it its own unique characteristics, which capture some of the subtlety of the physics involved in the problem. For this project, I explore 3 different models used in conjunction with 3 different loss functions. The first 2 models I looked at were 1D and 2D convolutional networks, whose architectures you see here. In the out block, you can see the use of multitask architecture. One task head learns to guess the relative weight of each component sigma, while the other learns the remaining parameter values. I also investigated using a multi-head attention, as depicted here, though in the interest of time, I won't go into the details of the mechanism. Before moving on to experimental results, I will note that the 3 loss functions. Loss 1 sums the losses from each task head. Losses 2 and 3 introduce a second term, which incentivizes the model to learn sigma with increased precision at 0 frequency, as this is very important and the hardest aspect of the sigma to predict. Loss 2 gives this a 1/10 of the total weight, while loss 3 gives it an equal half. Below the losses, you see sample results. The first 2 graphs show the plots of the targets and then the predicted sigma. And the third one in each cell shows the ratio of the true to predicted sigma value at each frequency. We would like this ratio to be as close to 1 as possible for all values. For context, the left example is an average to good prediction, while the right one is a very bad prediction. To summarize the results, I found most interesting and promising behavior to be exhibited by the 2D convolution and the attention models. The attention model proved to be the most robust, generally making reasonable predictions regardless of the loss function or changes in the dataset used in training. The 2D con was quite interesting as it gave the single worst performance by any model by far when paired with loss 3, but it did as well, if not better than the attention model when using loss 1, which did not add physical constraints.